everyone, today I'm going to be going over question 5 from spring 2017. It's going to be a linear program, and we're given m different types of food, f1 through fm, that supply nutrients n1 through nn. The sort of problem is as following. We need Cj of nutrient j, or nutrient nj. Bi is the price per unit of food fi, and aij is, or sort of A is this 2D matrix where aij tells us the amount of nutrient and j contained in 1 unit of food fi. And so we need to write a linear program that plans a meal by meeting all the requirements, so meeting all the CJs, while also minimizing the cost, which is, let's mark it as red, minimize cost BI. And we're going to define all variables we use. Okay, and so I guess the first thing you should do when you look at this problem is you need to spot sort of what you think will be the objective and what you think will be the constraints. So from here, we can see that we're looking for the minimum cost. So BI is going to be involved in our objective. We'll mark it objective. And CJ is the minimum daily requirement. So that'll be, naturally, that'll be the constraint. Since you need to meet the requirement, but as long as you met the requirement, you don't care about having more of these nutrients. Now, what variables are we going to have to define to solve this problem? That'll be part A. So naturally, what we need to do is in our problem, we'll create variables for how much of each food we get. So we'll call it X, and we'll call it XI, since to mimic sort of FI here will be the amount, or number of units of FI. So basically all of these XIs are going to be multiplying the price per unit food, because to calculate the total price, you need the number of units multiplied by the price per unit. And they're also going to be multiplying this sort of value here, aij, which will be the amount of nutrients that you get for food xi. So given that we sort of talked through this, let's define the constraints mathematically. Well, we'll start with the objective. So the cost for us is going to be given by the cost of sort of one of these food items is going to be xi, the amount of that food item we get, multiplied by bi, the price per unit of food. And as always, we need to sum over all of the food items. So summing from I to m, from I equals 1 to m. That will be our constraint. We'll just mark it red. Now, that'll be the objective. We'll mark it red. Now for the constraints. Since the constraints involve the minimum daily amount of nutrients, we're going to have, we're going to need to meet at least Cj amount of nutrients for all j. And for all j from 1 to n, this will be this sort of a little shorthand notation. And what is going to be the amount of each nutrient that we get? Well, we're going to see how much each food item contributes of this nutrient. So we're going to need to sum over all the food items from 1 to m, and aij is going to give us how much of that food item we get, or how many nutrients we get for this food item of type, how many nutrients of type J we get for this food item, and then the amount of this we buy is going to be xi. And so now you see that sort of the amount of nutrient J that we're going to sum over all the food items, multiplying it by the amount of food that we get. And so that's going to conclude our sort of linear program. What we did here is we defined xi, which was an LP variable for the number of units of fi. What that does is it sort of multiplies bi to form the total price and multiplies aij to form the total amount of nutrients of type J that we get. And then we're given, in the problem, we're given these xj and bi, or sorry, cj and bi, objectives and constraints that we need to, formulate in this LP. Hopefully that makes sense. Now I'll go over some tricks for LP. Pretty much, you can feel free to pause the video, and what you need to do here is you need to take this sort of, tricky LP, nonlinear LP equation and formulate it as, a combination of linear LP constraints. Feel free to try this on your own. I'll go over sort of how to do this. So, for I guess part 1, we need to be able to express A as greater than or equal to absolute value of B. So sort of if B is -5, right, A has to be greater than 5. And if B is 4, then A has to be greater than 4. Now, what you can actually do here is you can rewrite it as a sort of combination of two regular LP constraints, as A is greater or equal to B and A is greater or equal to -B. Now, the reason you can do this is because if B is positive, then this constraint will dominate this constraint. And if B is negative, then this constraint will, strictly dominate this constraint. And you can say that as for either case of B, negative or positive, as long as one of them is enforced, the other one will always be enforced. And so essentially you're getting sort of this little constraint fulfilled for you. It'll be really similar for part 2, where we're going to be able to define 2 LP constraints that'll sort of act as this one constraint. Now, what we need to do here is define 2 constraints such that if one is satisfied, the other one is always satisfied, and that together has a property of being the min of BC. So what we can simply do is make A less than or equal to B and A less than or equal to C. Once again, depending on which one of B or C is smaller, we're going to satisfy one constraint and have the other one be sort of more loose and therefore be automatically satisfied. So I guess I'll go through an example where if B is less than C, this constraint here is going to dominate, and this constraint is going to be automatically satisfied. And part 3 is going to look exactly like part 2, where A is greater or equal to B and A is greater or equal to C. So if B is greater or equal to C, if B is greater than C, then this constraint is going to dominate and this constraint is going to be automatically satisfied. Yeah, hopefully these tricks will be useful for you on exams and homework problems. Definitely keep them in mind. They're super useful for formulating LP problems and allow you to take a sort of nonlinear problem into a linear space. Yeah, hopefully that was useful. Have a good day.